Welcome to another episode of Notable Perspectives. I'm your host, Dr. Muthu Alagappan, and today we're joined by Kevin Huang. Kevin serves as head of data and machine learning for Notable, where he leads the development of the company's intelligence platform, starting in the early days of natural language processing to now incorporating large language models. Prior to Notable, Kevin was a data science technical lead at Change Healthcare. He holds a PhD in electrical engineering from Stanford University, where he built computer simulations and new algorithms to study nanoscale LED devices. Kevin, welcome to the show. We're very excited to have you on.
Very excited to be here, Muthu.
So I want to jump right in. This is an extremely exciting time for the field of artificial intelligence, but also for technology overall in terms of the new capabilities and opportunities that exist. So I want to start, sort of at the very highest level. So Kevin, in simple sort of layman terms, what is artificial intelligence, and what could it mean for healthcare?
The way that I like to think about artificial intelligence is that it's a general field or a study of making machines, quote unquote, intelligent. Now, the question is, what is intelligence? And the simple way to understand this is anything that we do to, for example, make decisions, recognize information, understand meaning out of information. All that can be categorized as intelligence. So this covers basically human cognitive work. So the field is really about making machines, giving machines the ability to perform tasks that normally requires humans to do, especially human cognitive abilities to do. In terms of what this could mean for healthcare, obviously in healthcare we process a lot of information, anything from clinical documents, signing someone in or registering someone for an appointment. So all this requires cognitive work to make decisions on if this patient can see this doctor, or is this insurance applicable in this situation. So all this type of decision making, dealing with clinical documents, language, or fax documents, performing categorizations of where this document should go, where it should live in the EHR, all this is intelligent work. And so the implications here is that it is now possible to automate a lot of this very manual work because our machines are getting better and better at performing a lot of these cognitive tasks.
Great, that's very helpful. And so we often hear the term AI ML sort of hand in hand. You helped us define artificial intelligence as sort of teaching computers or machines to be more intelligent in sort of a human cognitive type way. What is machine learning then? Are they the same? Are they different? How should we think of AI and ML together?
Right. So machine learning, I would think of as a method or a tool to achieve artificial intelligence. There are many ways to do it, and machine learning is one of them. In the early days of artificial intelligence, almost all the systems were built by humans, diligently coding in rules or knowledge into the machine. And the machines would then use that information to process the data. But as you can kind of imagine, that's a very laborious and time-consuming process. So you need a lot of humans just to make something simple work. Now comes along machine learning. So machine learning is a methodology where essentially you allow the machine to learn by itself. From what? The question is. And that answer is that it learns from the data that it observes in the real world, or data that we feed to the algorithm that's doing the learning. So in a sense, we're no longer explicitly stating what these intelligent machines should do. So given input A, it should output B. Instead, we allow the machine to observe what's happening in the real world, and it can infer patterns or ways of operating directly from data that it's seeing. So in a sense, it's giving up some control over what the machine's learning, but we're gaining a ton of more scalability and generalizability. So we don't have to have, armies of people coding up rules anymore. We instead just takes what's already existing, operating in the system, and say, here's the inputs, here are the outputs that I expect in these situations. Go figure it out. And it turns out, once you have a lot of meaningful data, that method becomes much more powerful versus the alternative.
So based on that, it seems like machine learning, is quite a bit more powerful than traditional deterministic programming. And really, most of the use cases in healthcare for AI will come from this machine learning sort of set of techniques. Is that how you see the world, or do you think there are still opportunities for great healthcare use cases that are
Mm-hmm.
non-machine learning but still within the AI umbrella?
Yeah, certainly. So machine learning is not the silver bullet to everything. There are cases where you may not have a lot of data, and so you still want experts to code in their knowledge based on heuristics. So that's number one. The second is that machine learning is, kind of a black box. So if you want good observability, understanding like why the machine made certain decisions, you may want to encode something more explicit into its behavior. Um, so I would see in all applications, healthcare included, that the best kind of intelligent applications will be a combination of decision trees, which people build in, plus machine learning that handles very complex, large amounts of data. So the hybrid between the two usually will deliver the best value.
So within machine learning, we hear about a lot of different techniques or concepts. So there's deep learning, natural language processing, just to name a couple. Can you help us just define some of these terms as we get deeper into this space? Maybe deep learning and natural language processing to start.
Sure, sure. We can start with deep learning, since it's like a natural extension into machine learning. So there are also lots of methods within machine learning to allow machines to observe data and learn from it. And deep learning over the past, say, 10 years has really taken off as the de facto method that gives us the best performance, and performance meaning, real world accuracy in terms of how it predicts the outcomes. Um, and deep learning specifically is, as the name suggests, model after the human brain. So the construction is such that you have many nodes that are kind of interacting and talking with each other, and the combination of which gives you a representation of the model that's, represents the real world. Um, so deep learning is especially good for complex data, such as images or text, which traditional methods, statistical methods, don't work as well on. And the reason is that in deep learning, you can scale up your models to very large sizes. So these nodes or neurons that I was talking about, you can scale them to millions or even hundreds of billions nowadays, in terms of size. And what that gives you is that your model can form very complex representations of the data. So, for example, in clinical data, obviously you have very rich representations. You have all the different diagnoses, all the symptoms that people can have. So in order to capture all that nuance, you need essentially a large brain, right, to process it. And so deep learning has been shown that as the model gets bigger and you feed it more data, it can capture more and more of that nuance within the system. Whereas traditional methods, statistical methods, usually, peters out at a certain size or performance. Now, going into natural language processing, in terms of, there are a couple of goals within artificial intelligence. One of them is to do with processing text. And I would say another field is computer vision, which is where machines learn to see, to understand images or videos. So natural language processing is all about machines understanding and processing text. In terms of processing text, you can think of it as anything to do with written language, spoken language, and the tasks that you can perform with natural language processing can include things like translation. You can maybe have the machine perform a document classification. Is this a referral document or a notice of admission? So you can look at the text and determine what type of text it is. You can also do what's called entity extraction. So within the piece of text, I want to find, maybe the patient's first name, last name. If it's an ID card, what's the member ID? So all these are to do with processing text information, turning it into something useful or meaningful for that context. But recent advances in natural language processing enables machines to do more than just these very atomic tasks. Now we can have machines understand instructions. So if you want the machine to generate a paragraph of text based on these 5 bullet points, or you can summarize a whole research paper into its highlights. So these are all kind of processing text information. And so you can see basically all of human knowledge, or most of it, is described with text or language. So this the ability for machines to understand and perform meaningful tasks from language is just incredibly important.
We'll get into large language models in a second and maybe how they have catalyzed the power of natural language processing. But, maybe prior to large language models, what were the limitations with natural language processing in a healthcare context? You kind of gave us some examples of where they were useful, but what were the limitations?
Right. So natural language processing has been around, I don't know, I'd say at least, 20, 30 years. As soon as computers are invented, people have been manipulating text and text strings. Now, in the early days, it's all mostly based on pattern matching. So we're writing some ability to find, say a verb before a noun, or making very explicit call outs to whether something is, a organization or an entity, or some field that you care about. But that takes a lot of human effort to program. So in the early days, the limitation is that you essentially have to construct, several steps in a natural language processing pipeline. First, maybe you have to segment a complex document, say into, the footer, or the title, and then some content. Maybe there's a section for, analysis and assessments. And then you have to take each paragraph and parse out, the critical information from it using a second algorithm or model. So you chain these, 3 or 4 models together to get your final outputs, which could be, a predicted diagnosis, or, a CPT code that you're interested in. So in this case, you can see that in a sequential manner, the overall performance is kind of dependent on the weakest link within this chain. And it also affects, like upstream tasks also affects downstream tasks. So overall, the performance is very hard to optimize, and overall, it just doesn't work very well. So, fast forward to today, we have essentially very generalized language models that takes all those tasks that I just described and have one model that performs them all in one shot. And that, first of all, simplifies engineering implementations tremendously. And also because of the amount of data that it has learned from, it can perform a wide range of language tasks with very high accuracy.
So that's a great segue. So let's talk a little bit about large language models. Maybe before that, I want to touch on this concept of transformer models or transformers. And so
Mm-hmm.
help us connect the dots between, traditional NLP, then we have these transformer models, then we have large language models. What is the progression? How should we think about this?
Mm-hmm. Right. So I described, back in the old days how NLP was done, essentially a lot of pattern and keyword matching and rules based on even grammar, right? So people need to code in specific sentence grammar in order to understand them. Now, in the mid 2010s, deep learning is beginning to take off. So these are based on kind of complex node connections that's inspired by the human brain, neurons. So transformer is an architecture within deep learning. So you can think of an architecture as the kind of the structure of these networks. Now, what's cool about transformers is, as opposed to previous techniques, is that previously, in the earlier days of NLP, I think people were trying to mimic how humans read using what's called recurrent neural networks. So recurrent meaning that the system is feeding back onto itself. So imagine, I'm reading a paragraph. I essentially read, word by word. And as I read sentence, I'm forming some understanding or representation of what this paragraph means as I read it word by word. So recurrent networks essentially does that, but only in machines. So they replicate it in machines. It turns out it doesn't work that well for very long paragraphs because essentially we have, the machine has limited memory. So by the time you reach the end, you kind of lose the information from the beginning of the sentence. So that was kind of the limitation of recurrent neural networks. And they were kind of slow because you had to read word by word. The innovation in transformers, which was published in 2017 by a team of Google researchers, is that they thought, well, we're just going to read the entire text or entire page all at once. So the model forms a representation of every word with every other word. So it's relationship of every word to every other word on the page. And it's able to learn, which word is related to another in this entire representation. And so you can process that entire information all in one shot. So it's faster and it gives you a better kind of results. So that's the kind of breakthrough with transformers. And I mean, these days, the state of the art, both NLP and also in computer vision too, are mostly all based on transformers. So transformers has also crossed realms into, understanding images as well because of their ability for parallel processing.
And so on the image side, is a transformer similarly looking at the association between one pixel and another, in terms of an
Mm-hmm.
analog of like one word to another word's position?
Right, right. So for images, you can think of this as like a two-dimensional map where you have patches of data, and the transformer essentially looks at whether how this patch is related to another patch. So people have very successfully transformed the usage of this model into that realm as well.
Okay, great. And so we're making good progress here as we sort of uncover these various techniques that have emerged over the last, several decades, which I think takes us to large language models. And so I have a guess on what this is based on how you've explained the other concepts, but we'll let you kind of walk us through
Mhm.
how these models got their name and what their relation is to transformers.
Right. So with transformers, you can apply it in many domains. And when people applied it to language, um, you can essentially think of them as the language models themselves. So what is the language model? So in the machine learning domain, language model is something or a model that tells you what is the probability of a particular word appearing under a specific context. So you have a sentence, I like to go to and the model can tell you what is the likelihood of the next word being, beach, which is very high, or, the grocery store could be also very high. But something like Mars could be a little lower. So it's a probabilistic model that tells you what is the likelihood of the next word appearing being X. And in the kind of learning of transformer models, this ability is kind of baked into the system, because what the transformer does is that it takes in, a text or a string or somebody's, conversation, and it will output, the next sentence like a response. So naturally, it has to know what is likely to be the response given this input. So that's kind of the principles behind what a language model does. Now, large is pretty self-explanatory in the sense that, since its invention in 2017, people have, just gone up the scale on building bigger and bigger transformers. Bigger meaning, more layers to the transformer. Layer meaning, it's like a taller building, right? We're stacking up these intelligent units on top of each other, kind of like a building. In 2017, maybe there's a 10-story building. These days, it's tens of stories. And it can also read a lot more text. So it's both tall and very wide. Wide meaning, back in the days, you may only be able to read, maybe a few hundred words at a time. Now, with large language models, you can read hundreds of words or even, thousands of words these days. So that's kind of the evolution of how we go from transformers to large language models. But the architecture is essentially the same. And once you scale up the model, you also want to feed it a ton of data. So in the sense that the data is, starting from, maybe a few books to these days, it's the entire, internet's Wikipedia, all the audio books that you can access to, all the social media threads that is being scraped. So all this data, when you combine with a large language model, it can form very complex representations and kind of encode all that knowledge into this single entity that you can then prompt and get responses from that is coherent and can perform a large variety of intelligent tasks.
Great, that's very helpful. So let me see if I can get this right then. So artificial intelligence is sort of teaching machines to be intelligent in a way that mimics humans. Of that, machine learning is a technique for that, where machines can learn from data over time, either in a supervised or unsupervised manner. Within machine learning, deep learning has emerged as sort of the de facto, best way to do machine learning, and deep learning mimics human neural network architecture, a series of nodes that are interconnected and sort of differentially weighted as they pass inputs and outputs through them. Transformers are an architecture of deep learning where you can sort of ingest a lot of data at one time and understand the association between sort of either patches or individual components of that data. And large language models basically took transformers, applied them to large bodies of text, really, really large in these cases, everything on the internet, from which emerged the ability to understand and sort of do semantic understanding and text generation in a really profound way. Did I get that right?
That's perfect. Exactly.
Awesome. So thank you for walking us through all of that. So I have a couple of, maybe, sort of more intriguing questions. One of them is just very basically, how did we get all of the words on the internet into a model? Like, is it easy to scrape the entire internet and every Reddit
Mm.
subthread and YouTube comment and blog post? Like, how is that possible?
Right. To be fair, it's not the entire internet. I think a lot of the data is, either repositories that people have prepared. So Wikipedia is probably a very well published one. There are kind of ebooks, repository of ebooks that is been around. A lot of data sets are kind of proprietary and private, so it's not something you can just go and scrape and get all that information. But in order to prepare the data set for large language models, it is a very time consuming process, and the quality of data that goes into it is extremely important. And as you can imagine, going through such a large body of text, it's hard to discover whether there are quality issues within. So people also develop techniques to inspect what's in a large body of text, cleaning it up. So based on our current kind of large language model architecture, a lot of the improvements are coming from having better data quality versus just more of it. Because, garbage in, garbage out applies, entirely here. So the better quality data you can feed it, the better that it performs. And, you don't get unexpected cases as often.
Next question on my side. So there was some buzz, I believe, on Twitter recently around this notion that maybe we've sort of reached the pinnacle of these models, and that GPT 6 or 7 or 8 is actually not going to be a lot better than what we have right now. That we're sort of reaching a natural limit to how good these models can get. Now, I'm curious to get your perspective. Is that true, or are we actually in the opposite form, we're just in the beginning of an exponential rise in how powerful these models will be?
Mm-hmm. Yeah, that's a very intriguing debate, which obviously I don't have perfect answer to. But from what I've seen and read recent articles, I think it's people are starting to see that simply making the models bigger isn't going to get us, the gains that we've seen in the past several years. So for kind of scale context, when Transformers came out, I think there were in the kind of hundreds of million, could be kind of a billion parameters. Parameters being, you can think of them as like number of neurons in this network. Kind of 1 billion is pretty large, even 3-4 years ago. Now, over the past 2 years, it has gone from 1 to 10 to now, 200 billion parameters. So that's kind of where we are today. Now, people don't know what GPT-4 is at. This hasn't been publicly announced, but I think within that range of maybe no more than a trillion parameters is possibly where GPT-4 is at. But that's, my uneducated guess at this point. But yeah, people are conjecturing that, going to 10 trillion, for example, may not give us better performance. So we're seeing some plateaus there. But what I think a lot of new innovations and improvements will continue on an exponential curve is all the engineering that goes into using an LLM. So what do I mean by that? So LLM is great for performing these language tasks, but it's only as good as the information that you give it. So the quality of the data, the quantity of data, the real time nature of the data that you feed it will be extremely important. And secondarily, large language models can follow instructions really well. So it then comes down to how you instruct it to do the task that you desire. So combining, real-time data and then very well engineered instructions, and then stringing it together into, very useful engineering systems, I think we will see exponential improvements in the value that this provides. So I think the base foundational capability is kind of already really good. And I mean, I could be totally wrong, but I think foreseeable future, it's not going to get 100 times better, but certainly you can use it in ways that is incredibly more powerful than what we see today.
So to summarize there, it sounds like we don't know for sure, but unlikely that the model itself will just be inherently 10 times better just because we over time feed it 10 times more data. But
Mm-hmm.
we think the models will improve based on instead the real time data that we're sort of feeding it for context, plus the way that we're instructing it or giving it prompts or sort of chains of commands, and that can actually improve performance quite a bit.
Yeah, yeah.
It's a great segue to my next question, which was, LLMs have almost democratized access to these extremely powerful language models where, almost anyone with some engineering background can now utilize and leverage this technology, which begs the question, where will the differentiation be between one LLM solution versus another in a particular use case? So in healthcare, let's say we're using LLMs to, a popular one has been automating prior authorization completion.
Mm-hmm.
Where do you see the differentiation lying between multiple different solutions in that space?
Mm-hmm. Right. So right now, the foundational language models are, widely available to anyone who has API access. So if you have able to write some code, you can access the outputs of these models and give it relevant information. So I think the differentiation will really come from two places. One is the vertical knowledge within the domain. So certainly you need to know what is the right thing to do under this situation, such that you can instruct the model to perform that for you. So vertical understanding, clinical knowledge or administrative workflow knowledge, all that is, even more important now than before. So having that deep understanding into the domain that you're trying to solve is extremely important. Now, second of all is, again, the access to the right data. So language models itself is kind of a knowledge base in which that it remembers all the information that it's read, maybe not perfectly accurately, but to the most part, with pretty high fidelity. But it still doesn't give you the right answers given the task that you're solving. So if you're looking at a patient's chart to answer some clinical questions for prior authorization, the publicly available model isn't going to know the information about this patient, right, to answer the questions correctly. So in order for the model to perform the task, you have to feed it, the clinical history that pertains to that individual specifically. And you also need to ask the specific clinical question that's in question to get that prior authorization approved. So the ability to integrate all these context and data for the model to perform in a well-defined way, also secure and such that it doesn't produce unintended contents. I think that's where differentiation will be, because we have to be extremely cautious of how we use these language models, as they can be used as generative in generative ways that gives you nonsensical or not accurate information. So we need to build a lot of validation and guardrails to make sure that it's operating under the right context, such that it's giving you the right results. Otherwise, we'll need even more people to review the data. That's not solving the problem.
We talked about prior authorizations as one potential use case here. You've been quite deep in this for several months. Curious, what other use cases or applications of this technology in healthcare settings do you think are sort of most exciting?
Yeah, the crazy thing here is like there are just so many. Everywhere you look in healthcare, there's something that can be dramatically improved with large language models. So I'll give you a few examples. So starting from like very basic tasks, which is extracting information from a piece of document. So you can be looking at a fax referral document. It comes in, in this like referral templates. Now you can use language models to find where the referring physician is, what the clinic location is, uh, what is the reason for this referral. So all that can be done by the large language model through what's called entity extraction. So you simply say, I want to find the patient's first name, last name, phone number, and it can produce a well-structured output for you to do patient matching and referral entry. So that's number one, just extracting information, very kind of basic tasks. Um, More complex tasks could be something like clinical trials matching. So clinical trials matching is the problem of finding patients that meet a certain criteria as described by the clinical trial or is excluded by specific criteria. Some of these criteria are discrete, meaning that you can find discrete fields that exist within the EHR. Some things like ICD-10s or their social history, whether they smoke or not. So these are easy to find with programming, but there are complex information that resides in maybe radiology reports or visit notes on somebody having complex heart conditions or is doing specific PT exercises, for example, that can exclude or include them into the trial. So large language model allows the machine to essentially read through a large number of documents very quickly. So we're talking, thousands or millions of documents in a very short amount of time to kind of find a needle in the haystack out of a large patient population. So that's kind of the other end of the spectrum where you can handle very complex queries and find a match within a large corpus of documents. But yeah, there are also many more examples.
I love that. Sounds like there's almost limitless potential in every sort of manual workflow we perform today in healthcare for LLMs to at least assist and potentially
Mm-hmm.
augment quite a bit of that workflow. So if I'm a health system, this is quite exciting. I want to be involved in this. Do you think health systems should sort of take the reins and start building these applications on their own, or do you see more value in partnering with organizations out there who are sort of focusing all their energy, purely in the space?
Mm-hmm. I think there's a couple of considerations here depending on the type of healthcare organization. Certainly, I think for you know specific organizations that have a large body of technical capabilities, there are probably chunks of LLMs that can be applied very quickly because these are publicly available APIs and capabilities. That said, the field is moving very quickly. Every couple of weeks, there's a new model coming out, new capabilities. So it's a question of whether the engineering team can kind of keep up with developments and best practices within the field. So it's a high velocity development environment. So if the organization is set up to operate well in that environment, I think it's possible to build some cool applications very quickly. That said, most likely because of the new information that's coming out, new releases, and also the amount of work that needs to go into validating model responses, making sure that all the information retrieval based on your own knowledge base is scalable, accurate, and fast. There's a lot of engineering specific to LLMs that needs to be built. So just my experience working on this is that because of the way the LLM operates and the best way to get value out of it, you do need very specific engineering systems to operate them with low latency and also targeted towards a task that you want to build. So it is not a trivial manner to build fully automated systems that are based on LLMs. But there are maybe smaller chunks that small engineering teams can start to take on.
That's helpful. And as I sort of hear you talk, it almost makes me think of sort of almost like a power tool for an analogy, like a chainsaw. Like a chainsaw could make cutting down a tree 10 times faster. But if you don't use it properly or sort of use the right techniques or safety precautions, it can also be very dangerous and harmful. And so incredible potential to speed things up, but also the potential to get out of hand if it's not utilized in the right way. So maybe as we wrap up here, maybe the last question for you. I like to usually end on something optimistic, but in this case, I think there's a lot of optimism sort of built into this technology. So maybe we'll actually end on something that's a little more critical, which is how should we think about the safety of this technology as we start to deploy it in large sort of use cases? And how, if at all, should this be regulated in healthcare settings?
So that is a question that we constantly think about, just because, first of all, it's a new technology. People don't fully understand it, both from its limitations of its capability versus its weaknesses. But we're learning every day on it. So in terms of caution, mainly around doing the legwork to understand and validate the model in detail. And by that, I mean doing a lot of testing. So testing is the key here. Because these are large bodies of knowledge where you can prompt it to give, to have it produce all sorts of different outputs, there isn't very well established evaluation methods yet. So first of all, developing good evaluation methods in these kind of open-ended question type of situation is really important. Certainly for more specific tasks like document classification or question answering, reading comprehension, these we can have good model testing and evaluation methods built in. So I would put a lot of emphasis there before releasing anything in the healthcare setting. So yeah, I think that the caution is around being fully aware of what the capabilities are in the setting that's the model's being used in, and be very diligent about testing edge cases, cases that you may not think of. Have internal users run it, try to break it. I think that process and that muscle is super important to build. In terms of regulation, I think this is certainly worth a ton of both public discussion and good forums to discuss, because it is early days in this technology. There are certainly many ways to use it in poorly, and that can lead to bad outcomes. So we need to understand what those are. Specifically, I think what's giving people a lot of concern lately is the use of what's called auto GPTs. So these auto GPTs are essentially intelligent agents that can take action all by themselves. So given an objective, you can have this language model essentially determine the task list. So it comes up with 5 things it needs to do in order to complete this task. And it has access to, say, the internet. It has access to functionalities. It can write and execute code or hit APIs that perform some action. So in these cases, the stakes are much higher, right? Because you may not have full control over what the agent decides to do. And the observability there, certainly you can have some, but it's not perfect. So in these situations where you have language models becoming actionable agents, that's where I think regulations should provide some guidance as to what these agents should or should not be able to do, if someone should review, their behavior prior to being released. So I think that's an important topic to continue to follow up on.
Fantastic. Well, I know we're out of time, but thank you so much, Kevin, for your joining us today and for sharing your insights and teaching us about this entire space. Extremely exciting, and really appreciate you joining.
Sure, it's been a pleasure. Thanks so much.